Okay, my clock says 12 o'clock, so I think we're going to get started. My name is Nick Leister, and I am a training specialist here at SolidWorks. I've been with SolidWorks for 10 years, which I cannot believe that it's gone that fast. I used to work out of the Boston office, but now I'm here in lovely Eagan, Minnesota. This picture of me and my family is not taken in Eagan, uh, just for reference. This was in Colorado. Now, this is the last presentation that we have in our webinar series. We started off rather simply with sketches and basic features, and then we've gradually gotten more and more complex over the last 3 weeks. And this is the culmination of what we've learned so far. And today we're going to talk about SolidWorks Motion and SolidWorks Simulation, which are tools to analyze your designs. And just for all of you who might be wondering, this recording will be made available after we're done here. It's going to get posted. So keep an eye out for that if you want to see that. Okay, so the first thing we're going to talk about today is SolidWorks Motion. Now, SolidWorks Motion is a rigid body dynamics tool. Um, the way that it works is it uses, there we go. Whoop. Oh, I wanted to show you guys the animation. This is actually what we're going to simulate here, what you see there. Um, the way that it works is it uses the existing assemblies and mates, and you use those to define motion within a motion environment. And this not only gives the types of animations that you see here, but it also gives more quantifiable data, allowing you to do things like size motors, assess force, analyze stability, and so forth. In today's talk, what we're going to do is we're going to use SolidWorks Motion to add gravity, to define contact. Contact has some material property characteristics. Um, we're also going to define motion drivers, which are essentially just motors, and we're going to analyze our results and more. Then what we're going to do is we're going to move on to SolidWorks simulation with a different model, the model that you see here. And SolidWorks simulation is a finite element analysis tool, FEA for short. And the difference between the two softwares is that Motion is a rigid body dynamics tool. The bodies don't bend and deform under loading conditions. They remain absolutely rigid. But with SolidWorks simulation, we actually calculate the deformations that occur within bodies. So what we can do is we can analyze how structures deform under various loading conditions. We can get stress and displacement plots and strains and this sort of thing for both parts and assemblies. And then we can use that information and redesign models, which is very easy to do because SolidWorks simulation and SolidWorks motion are fully embedded within the SolidWorks environment. In today's talk, what we're going to do is we're going to use SolidWorks simulation to add material properties, define fixtures, which are part to ground interactions. This is connections between the parts that we have modeled and the parts that we don't have modeled. We're going to define loads. We're going to use a force load in this case, but there are various loading types available, from temperature loads all the way to torque loads and pressures, that sort of thing. We're going to analyze stress plots. We're going to analyze displacement plots. And then we're going to use that information to make a quick change to our model and then reanalyze it to see how it affects results. What SolidWorks simulation allows us to do is to make parts both lighter and stronger at the same time. We're going to explore how to do that. And with that, I'm going to go ahead and get started. Now, before I do that, I have Joe Russo on the line. Joe, was there anything that I missed or anything that you wanted to discuss before I continue?
No, but there's already one question that I might need your help with.
Oh, okay.
Is the motion study of assemblies or only FEA? I think they're asking if you're planning to do both, and I think the answer is yes.
Motion studies are for assemblies, and SolidWorks simulation can analyze both assemblies and individual parts. In today's talk, what we're going to do is we're going to focus on analyzing a part just for time.
Perfect. All right, take it away, Nick.
Okay. So we have a familiar model. It should be familiar to you at this point. This is the KitBot model. Now, when we create simulations, both motion and SolidWorks simulation studies, one of the things that what we're essentially doing is we are creating a program that we run, that we execute, and then we look at the results. And just like any other program, you don't write the entire program, click execute, and expect to get anything worthwhile. That's not how that works. What you do is you start out simply, you build it and test it along the way. So one of the first things that we do when we create an analysis is we create a simplified version of the model, and that will save us computational resources. Here I have a model that I've simplified. I've removed a lot of small parts. I could have actually simplified this a lot more and removed all the parts that are below here, but this highlights the point. And what we're going to do is we're going to simulate coral, and coral is the term that's a part of the kit, the FIRST Robotics um, system, that the competition that you're running. Coral is the thing that you move in the competition. So I have coral here, and the way that SolidWorks Motion works is it uses all the existing mates that are available within the assembly. And as you can see here, there's a folder of all the mates that are a part of the assembly. What we're going to do is we're going to define a motor to rotate this component right here. And because of the mates that are defined, this component is going to move as well and going to kick the coral out. Um, now the coral, we don't want mated. In fact, we want it to be free to move around, but we want it to start out in the position in a good orientation where it's actually touching right here. Now, the way that we do that is through the mates command. You'll notice at the bottom, there's this option called use for positioning only. When I select that, and then I define a mate, what happens is that that mate does not appear in this list at all. In fact, I can pick it up and I can move it. It's not constrained. So this is one of the most handy things that you can do with motion is to learn how to use mates to position things, but not necessarily constrain them. I'm going to go back in and I'm going to define a couple mates with use for positioning only. So I'm going to pin this in, this property manager in, and I'm going to start by just positioning this guy on the face here. And then I'm going to use a mate that you might not have covered yet. It's called the width mate. I'm going to select it here. It's under the advanced tab. And I'm going to, the way that this works is I essentially select two faces on this component. And then in the second selection field, I select two faces over here. And with this center constraint active down here, it positions it directly in the center. And that looks good to me. So I'll unpin this and click OK. Now I'm going to take a look at motion studies. Now you'll notice that we have these tabs at the back, at the bottom, pardon me. Um, and when you create an assembly, you will have a motion study tab. I'll activate that and I'm going to get this warning message. This warning message often appears because what these tools available under the motion study allow you to do is to create animations where you control the position of camera views and so forth. We're not interested in camera views because this is we're going to create a motion study. But I'll show you what it does. If I click yes, it's going to reposition my view like this. Now, I don't really want to have this reoccurring as I'm setting my study up. So I'm going to turn off this feature by right-clicking orientation and clicking disable playback of view keys. And now I can move this around and switch between the tabs, and I'm not going to get that warning message appearing again. Now, now I'm going to create a motion study. To do that, I click this drop down right here, and I select motion analysis. Now it's not available right now. I only have animation and basic motion. These options are primarily for creating a visual display of what you want to see. Maybe that's good enough for you, but what SolidWorks Motion enables you to do is to get quantifiable numbers that are based off of calculations of momentum and force and so forth. And these are more just for visual representations of movement. So what I need to do is I need to go to my SolidWorks add-ins tab and activate SolidWorks Motion. Once that add-in turns on, what I do is I go to this drop-down and I can select Motion Analysis. It's now available. Okay, so this is the motion environment. There are a couple of components. I noted the tab here at the body to denote that we're in a different environment. I can always switch over to the model tab if I want to go back to redesigning something or something like this. We also have a timeline view right here. This timeline will fill in as I add features and functions. There's a tree here, and this tree highlights all of the parts and mates associated with the model. Remember, SolidWorks Motion uses those parts and mates to define the motion study. Now, we also have features running across here, and these are the motion features. What I'm going to do to start is I'm going to define gravity acting on this system. Gravity is this apple right here, so I'll go ahead and click that. And you can see there's an arrow indicating the direction that it wants to put gravity in. I'm going to choose the Y direction. It's pointed down. That's looking good. And when I click OK, the timeline updates to reflect that feature that I just created. Now, by default, the simulations that get created right out of the box are always 5 seconds long. I can change that by clicking and dragging this around, or by right-clicking this keyframe and clicking Edit Key Point Time. And this simulation that I'm going to create is going to be 3 seconds. It's going to be pretty short. And now I'll click OK, and the timeline updates. Now, this is a rather small timeline, so I can resize it using these buttons over here. What I'll do is I'll click Zoom to Fit, and it expands to the 3 seconds across this time frame. Now, like I said, when we create simulations, we're creating programs, and we need to test the programs as we write them. With gravity defined, what I'll do is I'll calculate the study and see how it behaves. To do that, I use this calculate button right here. When I click calculate, we'll see the study solve in real time. And what happens is that piece of coral drops all the way through the model, and it continues to drop over the course of 3 seconds. To that animation, I can replay by clicking play, play from start. But what I mostly do is I mostly click and drag this around which updates the model in real time as I drag the current timeline. So that drops. So the first thing I'm going to do now is I'm going to define some contact between this coral component and the rest of the components. I'm going to start out by clicking the contact option right here, and that's going to open the contact property manager. We're immediately presented with two options, solid bodies and curves. Curves are for specific situations, which I don't really have the time to get into now, but most of the contact that you define will be between solid bodies. I'll leave that selected, and then I will make my contact selections here. Now, I could just select this component, and all of these components as well, but this is actually rather inefficient. And the reason why it's inefficient is because this piece of tape will never touch this piece of tape. But by creating all of my contact in one selection, that's what I'm asking the software to calculate for me. I don't want to do that. I want to be efficient. So what I'll do is I'll clear this and I'll click Use Contact Groups. And with contact groups, what I can do is I can select the coral with the first group, and in the second group, make all my other selections like this. Now the software will not calculate how these pink components interact with one another, but rather how the blue components interact with the pink components. I'll scroll down, and we have the option to define the material that applies this, that's going to be associated with this contact. What this does is this changes the values for friction and elastic properties. But you'll see that they're grayed out here. If I actually just knew the friction and elastic properties because of tests that I've run, or maybe I looked it up, what I could do is I could unselect material and then enter in these values manually. I'm not going to do that here. I'm going to keep things simple, and I'm going to select the material option, and the materials are going to be acrylic and nylon. And now I'll click OK, and we have our first contact. So I'm going to go through the process of running it, testing it now. I'll click Calculate, and what's going to happen is it uses contact and everything, it just slides right off. These components, these wheels, don't stop the piece of coral. Okay, so that tells us what we need to do next. We need to define another contact condition. I'm going to do that again using contact groups, select the coral, and each one of these wheels. Now I'll scroll down, and this contact will be between nylon and rubber dry. And I'll click OK. Now I'll test this again. I'll click Calculate. And what's going to happen is it's going to roll, it's going to hit, and then it's going to stop. You can see a little bit of that friction cause those wheels to rotate. And there's no point in continuing this calculation because nothing's moving. So I'm going to stop this. You can always stop a simulation as it's solving by clicking the stop button. And then we only have results up until this point. Okay. Now, the next thing that I'm going to do is I'm going to define a motor to turn this gear. Keep in mind, this is simulating this motor right here. And the way that I'm going to do this is I'm going to have the motor not run for the first second. I'm actually just going to make sure that it does not move. And then over the course of 3 seconds, I'll turn on the motor and get it spinning and then turn it off. Okay. Now to do this, we go to the motor command. I'll select it. You can see that we have a couple different motor types. This is a rotary motor. This is the option for an actuator or a linear motor. Path motors are for if a part follows a curve or something like that. It's a very special type of motor. But what I'm going to do here is I'm going to select my motor location, and I'm going to use my G key on my keyboard to zoom in and select that edge. Now, I always have to figure out the direction. It looks like the direction is correct right now. This arrow points to the direction of movement. This is going to spin like this. Oh, no, it's actually going backwards, right? Yes, it's going backwards. So if it's going backwards, I can click reverse direction and it switches it around. Now we have to define how our motor moves now that we've defined the location and direction of the motor. You can see we have a couple of options. Constant speed will have the motor start running at the beginning of the simulation, and it'll continue at the same speed all the way through. That's not what we want. We want the motor to start moving at 1 second and then stop at 3 seconds, but not move from 0 to 1 second. There are a couple of options that actually allow us to do this, but the one that gives us the most control is data points. I'm going to select that. And this opens up something called the function builder. This allows me to define how the velocity of my motor and how it moves with time by creating a table right here. So for the start of the simulation, at 0 seconds, the motor isn't moving. Then at 1 second, it still doesn't move. But then at 2 seconds, we want the motor to start moving or to move. It'll reach its maximum speed at 2 seconds is what we're doing here. And then at 3 seconds, we want it to stop again. And this graph shows how our motor will behave, but it's not really giving us what we want. In fact, it's looking like it starts at 0, which is what we want, but then it starts to go backwards until 1 second, and then it goes forwards. The reason why it's doing that is because the software determines the points in between these points in the table with an interpolation, and it's using a cubic spline interpolation. I don't want that. I want a linear interpolation. Selecting that will give us exactly what I'm after here. And now I'll click OK and click OK here. And once again, I'm going to test this. I'm going to click Calculate. So it goes, it hits, it's not moving. And then at 1 second, it will begin to move. What we'll notice, though, is that the coral won't go anywhere. And this brings up one of the constraints of any rigid body solver that you use, whether it's SolidWorks Motion or anything else. And that is they are rigid body solvers. These wheels are actually designed to deform quite a bit to allow that those wheels to grab the coral, deform, and push it under. So it's not giving us what we want. So in this particular case, I'm going to go ahead and stop this. It looks like our system's operating as we want. I'm going to go ahead and switch configuration to a configuration I defined earlier called modified wheels, where the wheels are have this groove in them to allow the wheels to grab the coral as it's spinning. I'm going to go back and expand my tree here, and I'm just going to click Calculate. Now what's going to happen is it's going to hit, it's going to stay there until 1 second, and then the motor begins to kick up. Okay, so let's watch it. It's going to slowly start. At 2 seconds, it's going to reach its peak velocity. And we're hoping that that coral gets pushed out to the other side. It's moving, it's moving. While this is solving, maybe I could answer any questions if people have any.
There's just one that I haven't been able to answer, and it's about the light. Oh, I was talking right as the coral moved. Um,
Mm.
there's only one question, and it's about licensing. Somebody is trying to click along and they don't have motion. Do you know how somebody gets motion, or is it included maybe with SolidWorks Standard or Professional or Premium? What do you know
Mo
about the licensing, Nick?
Yeah, the motion is included with SolidWorks Premium. And if you're a commercial customer who's purchased either standard or professional, you won't have access to motion. You will have basic motion and animation. Um, if you're a FIRST Robotics team, they will give you uh, the premium by default, as well as any other products that you ask for the FIRST Robotics team. But that would explain why you don't see motion. You might need to have a different license of SolidWorks to access motion.
Perfect. That's the only open question, so I can hand it back to your presentation.
All right. So I'm going to drag this. It looked like it did everything that we wanted it to do. It scrolled down, the motor kicked up, it pushed it out, and then the motor stopped. So now that we have our setup, we can analyze our results. And there are a couple of ways to do that. What I'm going to do, I'm going to start by creating something called a trace path. So whenever we analyze results in motion, not only do we have the visual results that you see on the screen, but we also have the results in plots options. I'm going to click that right here, and I'm going to use this drop down. Trace path is under displacement, velocity, and acceleration, and trace path is the first option here. The way that this works is you select a location on the model. In this case, I want the center of this piece of coral. And so to get that, I will select an outer edge. And it shows on the screen a curve highlighting where the part is at any given point in time. It shows the path. So let's just take a look and see how that works. It goes through there. So this allows us to get an idea of, when you're creating your study, how close can you get this kit bot to the reef before you can turn on your motor? That's what this answers. So this gives a visual cue for that. But if you want a more precise um, set of numbers, what we can do is we can get the distance, but the z distance between this front face and the center of the coral. To do that, I'll go into result plots. I'm going to click displacement, velocity, and acceleration. And I'm going to take a look at linear displacement and the z component of linear displacement. And for this, I'm going to select one of these edges. And in the same selection field, I'll select this face. And when I click OK, a plot will appear, which I can resize. And this plot shows where we are at any given point in time, the distance between the z component of distance between the center of this coral and this front face. This is how you can get this quantifiable information. Okay, if I close this, the
Nick,
plots appear.
actually, may I interrupt real fast? Can you
Sure.
just say again where you found the trace path function? Somebody didn't see it, and I'm sure you could show it.
Yeah, it's result plots, displacement, velocity, acceleration, and then it's the first one, trace path.
Thank you.
Mhm. Okay, so the result plots allow us to get, oh wait, no, I'm sorry. I wanted to show that the plots are at the bottom here in a folder called results. You can access them at any time. Um, but you can also get components like forces, the amount of power required by a motor or the torque required by a motor. This system doesn't require hardly any torque. You can actually use a pretty small um, motor in this case. But what I'm going to do is I'm going to create a motor torque plot, and I'm going to select the motor in this selection field. And this will show me the amount of torque required at any given time by the motor to move things. And this gives a lot of jagged sort of results, but what this really shows is that friction and that contact apply most of the force. But you can see here the magnitude of the torque is rather low. So that's why we see all these little bumps. If we had to do something that required a lot more force, these bumps would sort of level off. But yeah, not much is required here. Um, the other thing that I wanted to mention is that you can size motors using this method, but what we're essentially doing is first we're controlling the motion, we're defining what the motion is, and then the software sort of works backwards in the sense that you define the motion and then the software will tell you how much torque and force was required by the system to get that motion. That's how motion works. Okay, that's it for motion. I was going to move on to SolidWorks simulation, unless anyone has any more questions.
None at this time.
Perfect. I'm going to close that down and I'm going to open up this grabber assembly. Now, this grabber assembly, it has mates and so forth. These mates do not transfer to SolidWorks simulation like they do in motion. Um, we have to define the connections between parts with different methods in SolidWorks simulation. In this example, maybe we have a piece of coral pipe that we'd like to grab. And as you can see here, this link one component, you can see the names of these components. This link one component, as I move up, that's when we come into contact with this pipe. Now, let's make a couple of assumptions. Let's say we're designing this grabber to go at the end of an arm that will go on our kitbot. One of the goals then is to make this grabber assembly as light as possible, right? Because if it's at the end of an arm, it'll be easier to control if it's lighter. And let's say that when we're grabbing this pipe, the load, the force that a motor applies to this end face is maybe, let's say, 15,000 newtons of force. And let's say that we're going to design all of these components with milled aluminum. Okay, so with that, let's take a look at how we can better design a specific component in this mechanism so that it's both lighter and can withstand the loads. We're going to analyze this component right here, this link 3 component. And let's just talk a little bit more about the loads. If we apply 15,000 newtons going up on this face, and if we assume that both of these link 2 components are perfectly vertical when the load is enacted, that means that this pin right here will transmit 7,500 newtons going up. And the same will be true on this side because this is a symmetrical system. Now this pin right here, this pin will represent using a fixture, and this pin will allow rotation because these systems rotate. And this pin will also allow rotation, but no translation. So that kind of gives an idea of the setup that we're going to apply to this particular part. So I'm going to open it up in its own window, and I'm going to define a simulation on this component. But before I do that, I'm going to get a baseline for how much this part weighs. To do that, you click the Evaluate tab and click Mass Properties. And uh-oh, something's wrong. The mass is super low. The density seems off too. Why is this? Because we don't have any material applied to this component. So before we define our simulation in SolidWorks simulation, let's define the material that will be associated with this component. I'm going to right click on this material, click Edit Material. And now I'm going to browse out to the aluminum alloys folder and select 6061T6. Okay, and this material has a mass density applied to it. So I'm going to click Apply and then Close. And with this material applied, now when I go into Mass Properties, we can see that its parts mass is 2.25 pounds. So what we're going to do is we're going to analyze this. We're going to see where it has weak spots, where we can potentially remove material, and we're going to strengthen this part in areas that it requires it and remove material where we can. So to get started, we need to create a simulation. And to do that, we need the SolidWorks simulation add-in active. Once I click this and turn on my simulation add-in, you'll notice that there is a tab that opens up on the command manager. This tab allows me to create a new study, which I'm going to do. Now, you'll notice, depending on your simulation package that you have, you might see all of these options here. These are for various simulation types. Getting into what each of these do might be beyond the scope of this webinar, but this analysis, this is going to be a static analysis. There's things are going to behave linearly, and that means that the material is a conventional metal with a yield point, and um, the uh, the loads are going to be below. They're going to apply. They're going to be below the yield limit, the stresses this part withstands. So I'm going to, with static selected, I'm going to name this analysis link 3 study, and then click OK. And now we are in the simulation environment. You know that we're in the simulation environment because the simulation tab is active across the bottom. We can always go back to the model tab, but when this is active, we're in the simulation environment. There are 3 main components to access features in the simulation environment. We have the study tree on the left, which I like to use. I like to start out at the top, filling things in as I go. That's the easiest way to go, as far as I'm concerned. We have the simulation command manager. This has access to all the features that we could need. And then there's the simulation dropdown, which also provides access to the same features. So to set up this study, we start at the top and work our way down using the tree. Now you'll notice that this top node, this link 3, has a check mark by it. This node defines both the geometry and the material. And because we defined the material within the model, it transfers to SolidWorks simulation by default. If I wanted to make a change to this material, I could right-click this node, and click Apply Edit Material. And this opens the material properties. If I changed the material here in this simulation environment, it would not affect the model environment. So that transfer of material properties only goes one way, from model to study, when you create the simulation. You'll also notice that the material properties here are now color-coded. This provides some insight into what SolidWorks simulation uses to when considering the material. It always uses the red material properties. There are also blue material properties, and these are required for very specific situations. So, for example, if I were to apply a thermal load where I increase the temperature of this part from 0 to 100 degrees Celsius, I would need this thermal expansion coefficient to be able to calculate how that part expands with the temperature change. So I'm not going to make any changes here. I'm going to click Close, and then I'm going to move down. Before I continue, are there any questions?
Nope, I've been keeping up with them. Keep going.
Okay, perfect. So we have this connections folder here. This is only for part-to-part interactions, but we only have this one part here. So all the interactions between this part and the rest of the environment are handled with fixtures. fixtures handle part to ground interactions. Now remember, we have a pin going through here and a pin going through here, and we represent those with fixtures. I'm going to right-click on fixtures, click Fixed Geometry, and make the selection. Now you'll notice here that there are these arrows. These arrows provide feedback into how the fixture operates. Fixed geometry locks all movement, translation, and rotation. What we want is a fixed hinge fixture, which allows for rotation, but no other translational movement. So I'll click OK, and the arrows remain. The fixture appears in the tree. I'm going to do the same thing, but this time go right to fixed hinge for this selection. Now I'm going to define the load. The load will act via a pin on this face. There are a couple of options where I can define the load, but the easiest way is just to define a force load. So I'm going to right-click External Loads and click Force. And I'm going to make my selection. These arrows also provide feedback. By default, if I make a selection, the load will be applied normal to the face that I select. I don't want to do that here. I want to click Selected Direction and define the direction where my load will act. I'm going to expand this link, and I'm going to select the top plane. And then down here, I can click Normal to Plane. These are just the directional components of the load relative to that plane. And I'm going to enter in my load value of 7,500 newtons. The arrows are pointing in the direction that I want, up. If I wanted to reverse them, the reverse direction option is right here. Okay. So now we have one more node left. We have the mesh node. And this brings up what the mesh is. The mesh is simply a collection of simple shapes that SolidWorks simulation can calculate the stress, strain, and displacement in. And it's really difficult to calculate the stress in complicated geometry. So we use simple shapes in its place and then use a mathematical matrix to calculate the stress and the displacement in all those small, simple shapes. A fine mesh will make smaller elements, which will have more calculations. It'll be more accurate, but a coarse mesh will be the opposite. Larger elements, fewer calculations, faster results, less accurate. I'll click Reset to make this go right in the middle. SolidWorks does a good job of figuring out what the mesh size should be, and I'll click OK. And then just like that, we have our mesh. Now we have our study all set up. I'm going to quickly go to run the study, which I'll do from the command manager. And the simulation doesn't take long to solve. And just like that, we have results. We're presented with three plots. The stress shows where the stress is on the model, and it also shows the material's yield strength. The yield strength is the point at which the material experiences stress so high that it cannot bend back to its original shape. The yield strength for this material is 275, and our highest stress is 131 megapascals. What this tells us is that we could actually double the load, which would then double the von Mises stress, and we would still be okay. So that gives us some good information. I'll go to the displacement plot. The displacement plot shows how far the part displaces from its original position. I can animate this, and we can see how the part moves. Now, this is showing an exaggerated deformation scale. It's exaggerated by 56 times. But what this allows us to do is to validate that our model is set up the way that we want. I'm going to stop this, click OK. And if I want to change it to true scale, I can right-click on the displacement plot, go to Edit Definition, and I can change the deformed shape to true scale And I can also change the units, for example, from this dialog as well. Then I'll click OK, and we can see that this is the true scale of the deformation. If I animate this, we say how little it moves. Okay, so this gives us a baseline. What I'm going to do very quickly, because we're coming up on time here, is I'm going to make a change to the model, going to the Model tab. With this option active, this option right here allows me to make a selection to see the dimensions of the part with any selection that I have. And it also allows me to make edits directly by clicking this little circle here. This is sort of like direct editing. I'm going to make this fillet larger. And the reason why I'm doing that is because most of the load was on this sharp fillet. Smoothing that out will improve the stress. I also have some features here that I have that I'm going to unsuppress. To do that, I'm going to select the top one, hold the Shift key, select the bottom one, release the Shift key, right click, and unsuppress. And this removes material from areas of the model that don't carry a lot of the load. Now, going back to the simulation, we don't have to set up the whole thing. The mesh and results are out of date because we've made changes to the model. But if I click Run this study, the software will automatically remesh and run the analysis. And what we have are some results that show the von Mises stress actually reduced, even though we pretty much removed material. So the part is now stronger. It can withstand higher loads. What I'm going to do here is I'm going to go to the Evaluate tab and click Mass Properties again. We can see the new mass is 1.8 pounds. That means that we've reduced our mass from 2.25 pounds to 1.8 pounds. That's a 20% weight reduction, and the part is stronger. So with that, that is what I have for SolidWorks simulation, and I'm free to answer any questions regarding simulation.
Nick, that was fantastic, both the motion and the simulation piece. And I'll just mention quickly some of the things you saw in the earlier webinars, such as basic sketching, basic features. Every CAD system is going to have those. But things that we saw this week, some of the things in SolidWorks Visualize, certainly some of the things in motion and in simulation, those set SolidWorks apart. Those are the reasons you want to make this your choice for your FIRST Robotics competitions team. So thank you very much, Nick, for showing those. Why
Yeah.
don't we switch over to the presentation and doing some of the closing items, and that a couple of more questions are coming in, but that'll give me time to read them.
Yeah, absolutely. Yeah, that's a good point. CAD is just one component of what SolidWorks is. But what you do with your CAD, whether you analyze it, whether you bring it into a different environment, however you do it, that switching is something that SolidWorks is really good at. These add-ins that SolidWorks has make it ideal for doing more with your CAD than other CAD programs sort of allow. Now, if you want to learn more about SolidWorks simulation, motion, we also have other analysis tools like SolidFlow, which allows you to see how fluid moves through systems. It's great for heat transfer and things like that. Um, or Plastics, which is a software that allows you to simulate plastic injection molding. We have training in all of that too. And if you go to My SolidWorks training, which is here, you'll see a collection of videos that we have on various topics. We also have access to CSWA practice problems here. The certifications are great, by the way. Certifications allow you to document how well you know CAD on your resume. It's a great system. And if you're into classroom training with a book and an instructor and so forth, we have that too. So these are the three options here. And if you're on a FIRST Robotics team, we give free SolidWorks to you. And with that, you can get, simulation, you can get flow, you can get product uh, tools to manage your data, um, and so forth. So if you're part of a FIRST Robotics team, make sure to check that out. Um, I love SolidWorks. If I, even if they didn't pay me to say it, I'd use SolidWorks for everything. So, and one more thing, if you made it through all six of these webinars, you'll get access to take the CSWA certification exam for free. There are three certification levels for conventional SolidWorks. CSWA is the starting point. CSWP is the next level. And then CSWE shows that you're an expert at SolidWorks. There's also certifications for uh, simulation products as well, which are separate. So make sure to check those out as well. And with that, um, I don't really have too much more to add. Joe, is there any
Yes,
more
a
questions?
number of analysis questions are coming in. So let me just briefly state we're at time. We're done with presentation. If you'd like to stick around to hear the questions, I think there are some good questions. We appreciate if you stick around, but because we're at time, if you also sign off, it won't affect your attendance for the CSWA voucher. Okay, with that said, here are a few questions, and it bounces all over the place as we might have expected at the end.
Mhm.
Someone asked a specific question for their assembly situation. A notification appeared saying redundancies in mates. Do you
Mm.
have a common answer to that? Do you know what that might be? Or is it assembly specific and we won't be able to answer?
It's a little bit assembly specific. We address it in the motion course that we offer. But what that is if you have two mates and they overlap, say, uh, a mate, by the way, constrains uh, any number of 6 degrees of freedom, right? You have rotational movement in three directions and translational movement in three directions. And you can define a mate to constrain 5 degrees of freedom, but if you also define another mate to constrain some of those same degrees of freedom, sometimes motion can give you uh, uh, some issues. Now, you can define your mates so they don't do that. That's one way to define mates to get around that. But you can also replace redundant mates with bushings oftentimes, which is a quick solution. A bushing allows for some slop in constrained mates, uh, so that the bushing allows for some movement outside of the double constrained area.
While I appreciate the full answer, I'm going to ask for faster answers because we have a lot coming in and we're already over time.
Oh, okay.
So, next one, how do I include an impact force, such as a ball falling on the ground, or I'll say when that coral hit the ground? Can
Mm.
I test what the impact force is?
Yeah. In SolidWorks, when you want to calculate the deformed shape of that impact, you would need to do either a dynamic simulation or a nonlinear dynamic simulation. This study was a static study that I showed in SolidWorks simulation, but for for an impact, you'd want to have some sort of dynamic option.
So yes, SolidWorks simulation can do it, but not just with normal motion studies.
Yeah, motion studies are nothing deforms. It's rigid body
Okay,
mechanics. Mhm.
thank you. Next, I'm going to just read it and let you interpret. Can you just show the stress value beyond the part that is affected?
Beyond the part that is affected.
My hunch there is you showed the stress on one part, but then does that part impart
Oh,
stress on the parts it connected to? And
yeah. So you can create studies of assemblies like we have here, like I'm showing on the screen. You'd have to create a simulation that involves those other parts, but yeah, um, you can create simulations of assemblies. Absolutely, that's how you would do it.
okay. And then I think the last simulation one that I'm going to do for you, and then I have to answer a couple. When you applied the directed force to the hole, did the force push on half of the whole surface, or did it also pull on the other half of the surface?
So it pulled on the other half of the surface as well. And the reason why it's a simplified um, loading condition. You can complicate things more by redefining or defining a different type of load, like a bearing load or something like that, to only apply to a specific region.
Okay, thank you. So let me answer a couple of questions because they're more logistics questions.
Mhm.
We are only offering a CSWA voucher to those that attended all six. We are not offering CSWP or CSWE or any other exam. Most of these webinars were about basic CAD, 4 out of the 6, so they only apply to CSWA, so that is the only voucher we are offering. Unfortunately, if you only attended 5 out of the 6 or 4 out of the 6, no voucher. You had to attend all six. This was the last of the 6 webinars. Some people saw your slide, Nick, about achieving the 6 out of 6, and they were hoping that more were coming so they could get there. This was the last in our series. And then the last question I'll answer is, will there be more webinars? These have been quite popular. These have been quite informative. But this is also the first time the SolidWorks training team has done a series of webinars like this. We really wanted to reach out to people considering SolidWorks for FIRST Robotics as they return to school in many countries around the world. But based on feedback and based on interest, we may have more, but there's nothing planned at this time. If I did not get to your question, I apologize, but I think I got most of them, and we probably should wrap up right around here.
Very good. Thank you for attending, everybody.
Thank you very much, Nick. You did a great job.
Thank you. Okay. Bye-bye.
Bye.